Welcome to the last lecture of this week. In this lecture, let us do some problems using the matrix method. So, let me quickly remind you what we did in the last class. By looking at the ray in a homogeneous medium, for instance, the kind that I have shown here on the screen, point P is represented by these sort of coordinates x1, alpha 1, x1 is the height distance measured from the axis, which is the red line here, and alpha 1 is the angle. So, ideally I would like to use tan alpha 1. However, because we are working in the paraxial approximation, tan alpha 1 is alpha 1. So, this is sufficient for us. What we actually used in practice was a quantity called lambda 1, which is mu 1 alpha 1. So, you could see that this should have been mu 1 sin alpha 1, again in the paraxial approximation it is mu 1 alpha 1. This is often called the direction cosine for a ray. So, using this we wrote down this equation for translation of a ray from point P to point Q. At point Q, the coordinates are described by lambda 2 x 2 and the initial point P is described by lambda 1 x 1. So, you want to know how to go from one to other. In other words, given lambda 1 x 1, how do I go to lambda 2 x 2, and that is provided by this solution in terms of this matrix. And similarly, one can work out a similar matrix for the case of refraction. So, imagine that I have this refracting surface which is flashed on your screen, and there is an incoming incident ray which gets refracted, bends when it goes into the second medium. So, then you define all these angles of incidence, angle of refraction, use the law of refraction. So, you can do all that, and finally, you end up with this matrix equation. X 2 lambda 2 is the point after refraction. So, you can imagine x 1 lambda 1 to be a point before refraction takes place, even ideally just before refraction takes place, and x 2 lambda 2 is some point immediately after refraction takes place, and they are related by this matrix S. So, clearly here you will notice that since x 1 and x 2 are 2 points on either side of the point where refraction takes place, and they are very close to one another, that you could take x 1 and x 2, which is the height from the axis, the red line here, to be x itself, basically a statement that x 1 is equal to x 2. So, this matrix S captures the effect of refraction. So, here lambda 1 x 1 is your initial coordinate, and then the ray goes through a system of optics where many things could take place, translations, refractions, several of them in any order, and finally, when it comes out, you describe it by lambda 2 x 2. Now, how is lambda 1 x 1 related to lambda 2 x 2? That is the question. So, in general, without doing anything, I could simply, so everything that happens inside your optical system is sort of encoded in this matrix. The determinant of this matrix, so if I call this matrix S, the determinant of this matrix is 1. First problem is something that we had done earlier on using the standard method. So, let me restate the problem. Let us say that I have this refracting surface, and this of course defines for me the axis, and I have an object here at O. I am going to denote this object by lambda 1 x 1. The ray goes and hits the refracting surface and gets refracted and reaches some other point which I shall call I, and this is denoted by lambda 2 x 2. And we shall also identify two other points very close to the refracting surface on either side. One which is just before the refraction would take place, let me call it A prime, and other which I shall call A double prime. So, the object is at position O described by coordinate lambda 1 x 1, it goes and hits the refracting surface. Let me call this distance u, and because the distance is to the left of this point P here, I shall give it a minus sign, and the distance from P to this point image I, we shall call it V, because x 2 is the height of the image at point I and the height of the object is x 1 at O. So, when you divide the height of the image by height of the object, you get magnification. So, it is simply x 2 by x 1, and once I know how these two are related, we can obtain many such information. And from here I have the other coordinate which is lambda prime x prime, which is just before the refraction takes place, and just after the refraction takes place the coordinate is lambda double prime x double prime, and from here finally I go to the loss point where the coordinates are lambda 2 x 2. Going from lambda 1 x 1 to lambda prime x prime, it is a translation, and from lambda prime x prime to lambda double prime x double prime, which is this, it is a refraction, and again going from lambda double prime x double prime to lambda 2 x 2, I have a translation. So, I have a translation, a refraction and a translation, and I know what kind of matrices will take me from one to the other. So, it is easier to do these calculations. So, let us first relate lambda prime x prime to lambda 1 x 1, and I must also state that we are going from one medium which is characterized by mu 1 to another which is characterized by mu 2. So, when I write the translation matrix, it involves mu 1. So, I have done the first part. Now, going from primed to double primed coordinates involves a refraction, and this once again is going to be a matrix for refraction. So, it will be 1 1 minus p here and a 0 here, and now the last part is translating from double primed coordinates to lambda 2 x 2. Since it is a translation, it will look like the first matrix that I have here, it will be 1 1 0. Now, it is happening in a medium whose refractive index is mu 2. So, that will be V by mu 2. As you can see here, you look at the last equation here, which is this. Now, here I have lambda double prime x double prime, and I can substitute for this vector from here, which is this, and here I have lambda prime x prime vector, which can be substituted from this equation. So, if I do that successively, I can directly relate lambda 2 x 2 to lambda 1 x 1. Let me write that equation. Now, to make it into a more simpler equation, all I need to do is to simply multiply these three matrices together. Then I can directly relate lambda 2 x 2 to lambda 1 x 1. Let me write the result, and now this directly relates lambda 2 x 2 to lambda 1 x 1. Now, we can analyze this and obtain the results that we want. So, now I have a relation that relates x 2 to x 1 directly. Now, if I have an object which starts off from the axial point, which means that it starts along this red line, the condition in that case would be that x 1 is equal to 0. So, the height from the axis is 0. In that case, the condition for the image is that x 2 also should be equal to 0. Now, if I put in this condition, when x 1 is 0, so this term will completely go away, and if x 2 is 0, since lambda 1 is not equal to 0, the only possibility is that this term should be equal to 0, which means that a small manipulation would give me the following result. So, it gives me this result, which is equal to p. P is simply the power, and if you remember, this is inverse of the focal length. So, that is mu 2 minus mu 1 divided by the radius of curvature of the refracting surface. Not surprising, this completely tallies with what we had derived before. To get a relation between x 2 and x 1 in the image plane or in the plane that is defined here, all I need to do is to substitute for p from what we had just obtained, and if you do that, I urge you to do it yourself and see what happens. You should, that particular element would go to 0 in the matrix. So, let me directly write the result. So, this would be the relation at the image plane. So, the relation that I need is x 2 divided by x 1, it is already there. X 2 divided by x 1 is 1 minus V p divided by mu 2, and if I substitute for p from here, what I have, I should get the following relation. So, this is my magnification. So, clearly if both the media are same, mu 1 and mu 2 would be same, they would cancel off, and it is simply the distance of the image divided by the distance of the object, sort of familiar formula that you would have seen earlier. Now, let us do the problem of two refracting surfaces. Ultimately, I would like to again go back to thin lenses problem. To start with, I shall have the following situation. So, I have two refracting surfaces, and this is my axis, and I have this point O which has an object, and this meets the first refracting surface at point P, and then there is refraction happening internally, in the sense that you can imagine that there could be even other refracting surfaces in between these two. But finally, when it finishes with all that, it starts from this point and goes down like this. So, the net effect of whatever is there inside these two system of two refracting surfaces has given rise to a ray which goes from O to P, and other one which goes from Q to I. I shall call this height x 1 and this height as x 2, and we also need two other heights. So, this one we shall call it as x prime, and this one is x double prime, and let us also define the distances. So, the distance from here to here, let me call it d 1, of course, I need to put a negative sign, and this distance we will call it d 2. So, the first point has coordinates lambda 1 x 1, and here I have lambda prime x prime, lambda double prime x double prime, and lambda 2 x 2. Now, I will not go through these calculations in detail, because it is nearly similar to what we did. So, we have one translation, then there is a refraction and a translation. Here I have written the matrix equation. So, clearly you can see this part which is translation, another one which is translation, and we are relating lambda 2 x 2 to lambda 2 x 1, but this one I have left it empty, I am going to fill it up now. But as I said, that determines what happens inside the system here between these two curved surfaces. So, let me in general write it as, so this you can think of as your system matrix, which encodes all the information about what happens in between these two refracting surfaces. So, after the multiplication, this is what you are going to get. Once again, if you remember, if your object is coming out of the object plane or from the axis itself, then x 1 is equal to 0, in which case of course, this last term would be 0, but x 2 would also be equal to 0, in which case the condition is that this quantity here is equal to 0. And this relation would give us, would tell us how d 1 and d 2 are related. Let us now define a refracting surface, work out the details and see whether we can use this particular relation to obtain the relation between d 1 and d 2. So, I have this thick lens here, object at O, the ray hits the lens at point P and then it comes out at point Q, and there is the image plane at position I. X 1 and x 2 are of course the distances or the heights with respect to the axis, which is shown as red line here, and the thickness of the lens is this quantity, which I will call as T. Further, I need to define these distances d 1 and d 2. So, this will be the distance d 1, and of course, I need to put a minus sign here, and this distance is d 2. The refractive index of the material is mu, and the radius of curvature of the left surface is r 1, and the radius of curvature of the right surface is r 2. So, as you can see, there are three components to it. There is a translation, and inside there is refraction, and then again translation. So, which means that if my image position is described by x 2 lambda 2 and object is described by x 1 lambda 1, they will be related through a product of three matrices. So, let me directly write the product of the three matrices. Product of these three matrices, let me use the symbol S to indicate that. So, if I take that to be this general matrix B minus A minus D C, this will be equal to the product of three matrices. This of course comes from my own calculations for this problem. Now, if I have to specialize to the case of thin lens, then I need to take the limit of thickness T going to 0. So, just put T equal to 0 in this matrix, and you should get this. And now, if you compare this with this matrix here, you can write what is A, B, C and D. So, to relate D 1 and D 2, we said that this is the condition, we derived it from this case of two refracting surfaces. So, if I substitute these A, B, C, D values there, I get the following equation. And now, if I substitute for P 2 and P 1, remember that we have these relations for P 1 and P 2. Now, I just need to put them in here, in which case I will get, and this one can equally be written as 1 by d 2 minus 1 by d 1 is equal to 1 by f. Again, it is a result that we had derived before from other considerations. This tallies with the previous relations that we had obtained. For the case of thick lens, I will probably not do the problem, but you need to go back to the full equation, which is this. So, you can't take the limit t goes to 0. So, keep this as it is, identify A, B, C and D, and then substitute them in this equation, and you should be able to get a relation between D 1 and D 2. This S, which is the sort of system matrix for the thin lens, can be rewritten in terms of the focal length or focus. Notice that 1 by D 2 minus 1 by D 1 is equal to f, which is equal to the quantity here. Hence, this equation or the matrix can be written as 1 minus 1 by f, 0 and 1. So, I shall stop this discussion of matrix methods here with these examples, but the central idea here is that identify what is happening between the incoming ray and the outgoing ray, and simply relate the two depending on whatever number of refractions and translations that happen. You know the matrices corresponding to each one of them, multiply them together, that will be your system matrix. And then using the conditions for where the image starts, where the object starts and image is obtained, you can finally relate x 2 and x 1 and obtain quantities like magnification and so on.